We're going to go up there and swap out 5 of these things. That's a big part of this mission, in addition to the keyboard porch and the crew transfer. And we talked to the guy who's kind of the battery czar for Boeing, Matt Fields. You talked to him.
Yeah, I talked to him over the press side.
Yeah, so let's watch.
You see these odd-looking blueberry things. Those are actually part of a very large battery that is going up, that's actually up on the space station right now. And I have with me Matthew Fields from Boeing. Let's bring him in just now. Matthew, very nice to have you again.
Thank you.
What do we have here? Explain this to us.
Well, this is what's called an orbital replacement unit. It's a nickel hydrogen battery. There's 6 of them per power channel, and that's why we're flying on this mission. There's 6 brand new batteries in the back of Endeavour right now. The reason we're flying 6 brand new batteries is to replace the old batteries that are in the Port 6 truss. They flew in December of 2000, so they're 8.5 years old. Nominal design life is about 6.5 years, but we didn't work these as hard as we had planned originally on the station. So they weathered quite well. They're meeting all their system performance requirements on orbit, and this is just the time we're going to replace them.
Now, how helpful is that for you to get 2 extra years of life out of these batteries that were planned for, about 6 years or so?
Oh, it's very helpful, and it's very encouraging. Part of the thing that's going to happen with the old batteries that we're going to bring back, we're going to take one and dissect it and do some studies on it and see how well it did up there, in hopes of see that they do much better than the design thought we do, and maybe we can extend station to 2020 without having to replace the batteries that we were just replaced again.
How tough is that? Going through batteries. I mean, you can't just go out to the Radio Shack and buy a couple of replacements. These are very specialized units.
Yes, they're very specialized. They're space rated. Obviously, very expensive. Like I said the other day, $3.5 million per box. But you got to look at what they got to do. They've been cycled 50,000 times, approximately, give or take. The Port 6 truss was dormant for a while we did a relocation of it, and so they weren't on the whole time, so we're back trying to do the calculation. I came up with 49,600 or something like that. So,
and what is the power requirement for this? How much power do we have to put out, and how long does it have to power this?
Well, each box is rated for 4 kilowatt hours. So it gets kind of complicated on how the station works with regards to the power. The solar rays create the power, and the batteries store it when you're in the sunlit portion of the orbit. And then when you're on the dark side of the Earth, in what's called the eclipse, the batteries then go into a discharge mode, and they supply all the power to the space station. So approximately the loading setup on orbit is approximately 12 kilowatts per channel. And they have more than ample power for that.
And show us with your hands how big this is. Can you do that?
Roughly speaking, they're about 4 feet long, about 3 feet wide, and about 2 feet high.
So much bigger than the average battery you'd find anywhere.
Yeah, and 370 pounds too.
How tough is it building something like this and putting all these together and then space rating it? Because this is not something you can just string together. It has to go through a lot of tests.
Well, the company that builds these cells you see here is Eagle Pitcher, and they've been doing it for years, and so they have the thing pretty much down, and they the processes and all that sort of stuff. I've unfortunately never been to the factory to watch them build one, but I have seen one with its lid off, and I have worked with probably about 100 of these. There's 48 of them on station right now, 48 total. And they, like I say, they're doing a magnificent job on orbit. They're meeting all their requirements, and it's going to be exciting watching the crew go out and physically take that big old battery off and put the new one on, and then we're going to bring, like I said, we're going to bring the 6 back with us.
How rewarding is that for you to see that actually happen? What do you think you'll be thinking when that happens?
Since my very first mission, which was the Z1 truss, every single one of them is rewarding. It's just incredible watching the astronauts work on it on orbit, and the hardware. You get excited. You go, oh, look, he's doing that or he's doing this, and so it's really rewarding.
I mean, the inner guts of this, so you'll be able to see every little part and what he's doing.
Well, this is what you're going to see on orbit. Is that guy right there? It's closed. It's got a blanket around it, so it keeps it warm when they're in the cold part of the orbit. And so that's what you're going to see on orbit when you watch the EVAs here in the upcoming week.
And you were talking about the possibility of having these batteries last longer on the space station. How realistic do you think that possibility is? I mean, what are the chances?
I don't know. I can't tell you that until we get these batteries back and take a look at them.
But there is that chance.
There's a chance, yes.
And what would that do to be able to have these batteries last longer? I mean, we're talking fewer replacements, fewer things to fly up there.
It would be fewer replacement, you're right. Right now we only have about, I'm going to say, 16 batteries left to fly. We don't have we need to come up with a way to do that if we need to go beyond 2020, if you will, if you wanted to extend it even beyond that. So, like I say, they're 370 pounds a piece. They're very heavy. You can only launch a few on, six at a time, based on space, and
And so 6 at a time you've got going up. Now, you think this will last? This is meant to last the same amount as the previous ones. Are there any changes between this unit and previous units that have gone up?
This is the same. We're still going to say 6.5 years, but we are going to hope for more.
Because since you got it out this time, and you said part of that was because you weren't being powered up the whole time. You didn't have to provide that power.
Part of it is we didn't cycle them as hard. When you go into the eclipse portion of the orbit, you go. It's called per state of charge. It's like you go up to 100% full capacity, you go down to about 80%, and then back up again. They're designed to go down to 65% and back up to 100%, and that's why we didn't work them as hard. Just wasn't as much loads required to support the station.
And where are you going to be viewing all this from? When you're seeing this mission actually fly, when we take off, when you see this mission flying, where are you going to be to watch the spacewalks?
I got to go look at the timelines, but I believe the EVAs are going to be in the afternoon and evening, so I'll probably be at my house watching it on TV.
All right, thank you very much, Matthew Fields. Appreciate it, from Boeing.